Hi, Peter. How are you doing?
Good. So we have 16 people. I guess it's about good numbers. We probably should start. Probably one more minute might be okay. Oh, but I can start introducing the speakers. So good morning. We have our virtual seminar today. I remind you the next time it's going to be in-person seminar, last of the year. And today we have a virtual one, and we have two talks from two students. The first talk is going to be from Shantanu, and then Shanxia Ren. Um,
Okay. So
well,
shall I start?
maybe let's move on. I wanted to introduce your title, but in fact you have your title right there. So maybe you just introduce yourself then, and
Okay.
then move on. Yeah.
Okay, sure. Hi, guys. Myself, Shantanu. I am a third-year PhD student in Boston University. And, before joining Boston University, I was a Pitt ISP student. I had to switch, unfortunately, from Pitt to BU because my advisor, Kehan, he actually moved from Pitt to BU. And prior to that, I did my master's in from University of Florida, and my current research interest lies in the area of explainable AI and multimodal machine learning. So today I'm going to talk about model explanation method. Now, there are always a dichotomy between interpretable by design models versus the post-hoc explanations. And in this talk, I aim to bridge this particular gap. More specifically, I'm going to talk about a method that will gonna incrementally carve out a mixture of interpretable models out of a black box. So why do we need a model explanation? There are several reasons for that. The first one is trust. When you want to relinquish the control and the objective of the training and deployment sites differ, understanding the model is necessary to engender trust. Another importance is causality. Now, all these AI models, they are just encoding the correlation. What if we can use the model explanation to generate hypotheses which can be tested formally with extra experiment? For example, in this paper, the authors use causal techniques to gain mechanistic insights into the genetic processes. The third reason is transferability. Can these AI models help us to build more transferable AI model? Because the clinical knowledge or the rules, they are quite transferable from one hospital to another. For example, say enlarged heart disease play a key role to identify cardiomegaly, regardless of the hospital. Our AI model, they are not so much transferable. We usually have to force them to learn the transferable pattern by learning across multiple domains. Now, can we leverage model explainability to make them more transferable? And the fourth point is informativeness. Now, if the AI is a part of decision making, then the only yes or no answer is not good enough. We need more insights of the decision making, like the clinicians. And finally, if we care about the deployment, we need to make sure that the decision making of these models to be fair and ethical. Now, these goes beyond the classical performance metrics like accuracy or the AUROC and stuff like that. I have to say that the ethical implementation of AI goes beyond the algorithmic fairness, but that's a different topic of discussion. Now, what are the general design choices? Practitioners, they usually have to, they actually have to decide between these two choices. They first create a black box and explain it in a post hoc manner, or they should go with a interpretable by design based transparent models. Now, example of post hoc explanations are feature attribution. There are many different feature attributions, for example, CAM, GradCAM, which highlights the important pixels which play a key role for the model's decision. For example, in this figure, in this chest X-ray, in order to say that this X-ray is having a patient of pneumonia, it is highlighting those red pixels. Now, For transparent models, there are like lots and lots of transparent models. For example, there are decision trees, there are linear classifiers, there are proto-PNet. But here in this work, we particularly focus on something called concept bottleneck models. Now, what is a concept bottleneck model? In concept bottleneck model, you feed in an image in a feature extractor, and then it will gonna predict some high-level concepts. Now, what do I mean by the high-level concepts? For example, say presence or absence of stripeness in a zebra can be identified as the high-level concepts. So the first goal is to use a feature extractor to predict the high-level concepts from the images, and then use a linear classifier, which will gonna take those high-level concepts to the final class label. For example, here, after training this model end-to-end, the concept bottleneck model is going to predict this image to be a horse, and it will also going to identify the top 3 concepts, long neck, forager, and buck teeth, which play a key role to identify this image to be a horse. Now, there are pros and cons of both of this approach. In post-hoc explanation, we have all the flexibilities of the black box, so the performance is not compromised. However, it leaves too much on explanation to the human interpretation, which is subjective and that are vulnerable to confirmation bias. Also, there are a lot of research that has shown that the post-hoc explanation can be inconsistent. For example, in this figure, at the very end, they randomize the final prediction, which actually predicts a garbage. But if you see that the saliency map or the feature attribution map is actually pretty similar when it is not randomized. And of course, no algorithmic recourse is possible. So if you see that there are some important pixels which result in misclassification, there is just no way of going back and fix the black box. Now, in this regard, transparent models, they support something called concept level intervention. For example, if you identify a concept is resulting the misclassification, you can go and set those concept values to a particular value, and this is usually done by a domain expert, which will gonna support this concept level intervention to fix the misclassification. And this is the biggest advantage of using concept bottleneck models. And in literature, this is called test time intervention. But however, we have very limited design choices, and these interpretable by design models, they are very difficult to design. And finally, they often attain the subpar performance compared to the black box variant. For example, in this figure, you can see that the concept bottleneck models perform way less than compared to the black box, which is a DenseNet 1-to-1 for identifying these diseases from chest x-rays. Now, what will be the desirable list of properties if we want? So what would be the desirable properties we want from a model? We like the flexibility and the good performance of the black box. So the performance of the model should not be compromised. The second thing is we want to support the algorithmic recourse, or we want to intervene and fix the undesirable properties. And the third thing is transferability. Now, for transferability, we mean that we want to extract some clinical rules from these transparent models, which will be domain invariant, so that these models can be transferred from one domain to another. So by transparent rules, we're gonna look something like this. For example, one rule may be if the fasting glucose level is greater than some threshold, which is 126 in this case, this will gonna result in diabetes. Now, these rules of like P implies Q can be written in a compact form in the form of, say, first order logic. And we want to extract these rules from our interpretable model. So the general idea is...
Shannon, could you get back? Just the question is the non-compromising performance. The question is what you consider as performance. Are you considering cross-validation on data sets as a performance? Because the real performance is to what extent you can convince the physician that is the right case and explain it to him. And in many other domains, there was a very clear evidence that weaker but more transparent models, which not as good on cross-validation, still perform better in human AI tandem, right? So it doesn't matter the AI is really that good by itself. what really means that the pair of AI and human doctor in that case perform better. So that's exactly the question. What is the performance? Is the ultimate performance of the doctor who get that, or it's just cross-validation?
So this is like the example of the performance of the doctor, the clinician, and the model. So we want the model. So we want to measure. So that I'm gonna discuss in my upcoming slides. That
okay. So
yeah, I think this will be clear in the upcoming slides. So so what we want is that, for example, say at the test time you will gonna get 100 samples. So out of those 100 samples, maybe the AI model will be good for 95 samples. And then those 5 samples, it will gonna say, okay, I'm not so sure about those 5 samples. Let a clinician to decide that what is the disease. So that I'm gonna discuss in the upcoming slides. So now what is our general idea? Now the general idea is, what if we could start with a black box model and then incrementally carve out the interpretable model in the form of, say, first order logic that I showed you the last slide. We will continue this process so that the contribution of the black box will gonna reduce at every step. And then finally, at the end, we will gonna end up with a set of transparent models, which we sometimes in this talk refer as symbolic models, because it uses the human understandable concepts or symbols and combine them to a symbolic function, which is here is a first order logic. Now, let me first explain you the setup. We are assuming that on the training data, we have the image and the class label and a set of attributes. For example, in this case, the set of attributes are the high-level concepts or the high-level features. For example, in this figure of dog and cat, the high-level concepts are 10 ears, shortened muzzle, and the round feet. And we assume that we have the ground truth attributes for all these concepts. And also, we assume that the black box can be divided into two halves. One is the fee, which is the feature extractor, and another is the classifier. So the feature extractor can be thought of like all the convolution layers, and the classifier can be thought of the final classification head. Now, this can be extended to the chest X-ray setup, where we assume that for one particular image, we're gonna also have the radiology report. And we can parse the radiology report with the help of any NLP-based pipeline. For example, here we use Stanford RadGraph-based pipeline to extract the ground truth concepts. And finally, we create the triplet where we have the image, the ground truth concepts, and the final disease label. Now, remember that we start off with a black box model. The idea is that the black box encodes the concepts in the intermediate layers. So the first step is to discover the concept. Now, this can easily be done by training a simple linear classifier, which we're gonna project from the activation space to the space of the concepts. Here, they are represented by this toggle bar to show the presence or absence of a concept. Now, this linear projector, T, predicts the probabilities of the concept being present in the image, and these probabilities will be the inputs to the downstream interpretable models. So what do we do when we discover those concepts? We try to find a rule in the form of a first order logic, combine the concepts or the symbols and mimic the behavior of the black box. However, these rules are very simple and work well for a specific data subset, and they are not generalizable for the whole data. So we borrow our idea from the so-called deferral model, which are represented as the selector here. The idea of the deferral model is like this. Say we want to deploy an AI model in a clinic. The gold standard is the clinician's recommendation, for example, the radiologist. Now, the deferral model is a probabilistic binary classifier that can be viewed as a selector, which will gonna choose between the AI and the radiologist. When it is very confident, it uses the AI model. When it is not, it defers the decision to the radiologist. For us, the selector is a classifier. It's a binary classifier, which will gonna choose between the symbolic model and the black box. When it is confident, it uses the symbolic model. When it is not, it defers to the black box. In this work, for each of these interpretable models, we have a budget, say 10%. So it means that this one particular interpretable model should at least cover 10% of the entire data set. Now, whatever is remained, we refer to them as the residual. So we copy over the initial feature extractor of the network and optimize the last layer of the neural network to specialize on the residual data. And this process, this will gonna generate the black box for the subsequent iterations, and we continue this process. We extract the concepts, we train another selector and a symbolic model to cover new portion of data. There will be some residual left, and we continue the process. Finally, these interpretable models G1, G2, G3 are the symbolic models that are extracted during the different phases of the process, and each of them are referred as the expert on that specific data subset. As a result, we end up with a mixture of experts, each of which are simpler functions covering specific subsets of data. And there could be a small residual left that cannot be covered by any of these, and we view them as the unexplainable part of the data. Now let's see one example on the COP dataset, which is a bird dataset. And here the concepts are like color, chest, or wing, or shape of beak. Now at test time, say these 6 examples, they came into our model. Now the first expert, we're gonna cover these 4 samples and use breast color gray and tail pattern solid as the identifying concept to classify them as the olive-sided flycatcher. Whereas expert 2 uses underparts color gray and wing color gray to identify this particular sample as the olive-sided flycatcher. And finally, this particular sample will be covered by the final residual, and it will gonna be unexplained. So here the takeaway message is specific expert, they look into specific subsets of data and they discover the local concepts which will gonna be important to classify that particular subset of data. Now, if we compare the performance, so here in this plot, the y-axis is the accuracy and the x-axis are the different models. Now here, first the black box is trained with vision transformer for top 200, and this 92, and it attains a 92% accuracy, which is indicated by this line plot. Now you can see that our model kind of overcomes or outperforms all the different interpretable based baselines, and the performance gap between the black box and our model is the minimal. And the same story continues for the ResNet based convolution based black boxes. Yeah, you can see that the performance gap between the black box and our model is minimal as compared to the interpretable based baselines. Now we can see the same thing for chest X-rays. So for example, these 4 samples again come to our model during the test time. Now expert 1, it covers the second one, and it uses left pleura, right pleura, and pleural unspec to classify it as pleural effusion. Whereas expert 2 only uses right pleura and pleural unspec as the classifying concepts or the classifying anatomies to classify the first sample as effusion, and like we can continue. And the same story continues for the performance plot for chest X-rays as well. Okay, so now in the second half, I want to talk about one application of our method. So it seems like that we created another explanation method, but now the thing is that how can we use that in a real world setting? So we use our method in a real world transfer learning setting. So for example, here, in a typical transfer learning setup, we train our source model on the mimic-cxr dataset in order to identify pneumothorax. Now we want to transfer this model on the Stanford CXR, and we fine-tune on the entire dataset of the Stanford CXR. And by fine-tuning, I mean that we are fine-tuning all the different components like the feature extractor and the classifier of the black box for this transfer learning. Now, this entire thing is data and computationally inefficient. Why it is data inefficient? Inefficient because you are using the whole Stanford CXR data set, which is huge. Why it is computationally inefficient? Because you are fine-tuning the feature extractor, like all the convolution layers and the classification head. So this is also computationally inefficient. Now, in the last slides, we saw that we extracted the clinical rules, which are like the anatomical and the pathological rules. Now, these rules, they generally are invariant. So can we leverage those rules to overcome this inefficiency in terms of data and computation? So how do we use that? How do we fine tune to a new domain? We assume that on the target side, we have very limited labels or very limited disease labels, and we also don't have the access to the radiology reports to parse. So it means that on the target domain on Stanford CXR, we don't have any ground truth concepts. So the first goal is to get those concepts for all the samples. Now, here is what we do. We assume that we have label of a very small portion of the patient, and this label is the ground truth disease label. So we apply the source model on the label data in the target domain. And the source model will gonna classify some samples correctly, indicated by green, and some samples, it will gonna misclassify some samples, which will gonna be indicated by red here. We look into the concepts that are extracted for those correctly diagnosed samples, and we assume that those are the true concepts because the rules we extracted work well for them. For the other cases or the misclassified samples, we don't know the concepts. Now, this is a typical semi-supervised learning setup, and we use any off-the-shelf semi-supervised learning algorithm to create the pseudo concepts for all the different samples, and we propagate the concept labels by fine-tuning the concept extractor fee. And once we have got the concept, we only update the selector and the interpretable models for 5 epochs only on the target domain data. Now, it is important to know that these interpretable models, they are very shallow one-layer neural network. So the computation cost to train them, or rather to fine-tune them for 5 epochs, is very less. So here is some result. The y-axis is the performance or the AU-ROC. The x-axis is the percentage of training samples that we used in Stanford CXR. So in this experiment, we train a black box on mimic-cxr. We extracted our models, a mixture of interpretable models from mimic-cxr, and we aim to transfer the black box and our interpretable model to Stanford CXR to see the performance gap. Now the y-axis is, of course, the AU-ROC or the performance, and the x-axis are the percentage of training samples that are used from Stanford CXR to fine-tune. For example, here we use only 2.5%, 5%, 7.5%, 10%, and 15% of the training samples of Stanford CXR to fine-tune our model and the black box. And now from the plot, you can see that, so this gray line is the black box performance, and with less and less amount of data, you can see that the green and the blue plot, which is our model's performance, is way better than compared to the black box. And this is very prevalent for other diseases as well. Now, as I mentioned that, fine-tuning the black box can be computationally inefficient because you are fine-tuning all the convolution layers and the classification layers. So you can see that in this particular plot, where the x-axis is again the percentage of training samples and the y-axis is the computation cost in terms of the flop count, you can see that the performance, the computation cost of the black box is very high, indicated as these gray bars, whereas for our model or the interpretable models, they are like shallow models. So the computation cost in order to fine-tune from one domain to another is very less, and we only fine-tune them only for 5 epochs. And this is actually continues for all the remaining diseases for Stanford. For example, in cardiomegaly, I think the performance gain is what we observed is highest, where the black box plot is this. and our interpretable models performance is this. So as a conclusion, post-hoc-based approach allows the use of flexible black box models, but post-hoc explainability is problematic because they are not faithful and it doesn't allow recourse. Interpretable by design model, they allow recourse, but they suffer in performance. Now, in this work, we carve out a mixture of interpretable model from the black box, which actually offer the best of the both worlds. And each interpretable model or the expert is modeled as a first order logic, but other choices are also possible for the interpretable models. For example, someone can use protopinet, decision tree, logistic classifier, whatever they want to use. And transfer learning is more efficient in terms of data and compute with our new model. And intervention is possible with a new interpretable model. Now, in our paper, we showed, a lot of this like test time intervention, completeness score metric to showcase that our model actually kind of performs way better than the baselines. And there is also another application which we showed, which is the spurious correlation, the elimination and detection of spurious correlation. And these are the papers where we discuss, all this work. And finally, I would like to thank Kay and Kehan to guide me in this project. The project website is already up there, so you can take a look. And thank you.
Shantanu, thanks a lot. I think it's really exciting work, especially that you kind of combine the old tradition of expert system, which has symbolic explanation, with the modern deep learning. And expert system is what started our program at ISP. If you know that's the great expertise starting our program was actually in the expert system, 2 generations of AI behind, and you bridge that together. Wow. Okay, could you just get back maybe to the slides? Or maybe you can share the slides, because it would be nice for people to.
Yeah,
okay,
I'm sorry.
Opening for questions. We've been a bit late, so we get about 3-4 minutes for questions. And please, we can get the slides shared. So don't ask simple question about the slides. We'll share it with everyone. All right.
Okay. I'm gonna share the slides. Okay, let me just. Yeah. Are you able to see the slides? Or no?
I think yes. No, not yet.
Yeah. Let me.
Yeah, sharing it in the chat is a good idea. Yeah. So Daniel, I guess you first. Yeah, I see your hand.
I'm gonna share the slides to maybe Michelle. And
oh yeah, so you can send it to Michelle. Michelle shared with everyone. Yeah, sounds good. Don't waste time now. Okay. So Daniel, you first.
So my question is about the performance evaluation. I know you had a slide that showed the black box model's accuracy, and then also showed that the existing and explainable model accuracy, and how your model exceeded that accuracy. Yeah, that slide right there. Like something like this was, so my question is, like, this shows that the performance on the accuracy is almost at the level of the black box. I'm curious how to compare the techniques of the explainable models in terms of their explanations. So this shows that like the accuracy is as high as the black box, but the question is, how does your model compare to the others in terms of the explanations it gives? If there's any kind of.
So due to the course of time, I actually didn't include those metrics. So if you go to our paper, so in terms of the explanation quality, we use a metric called completeness score, which will gonna give us it will gonna explain the variance of the concepts that are identified from our model and from the baseline model. And we showed that as our model is focusing on local samples, like on specific data samples, we achieve far better completeness scores. That's the first metric that we used in our paper. The second metric is what we used is, for example, say we identify these concepts as the most important concepts. What we did is that we manually go there and set the values of these concepts as zeros, and we record the performance drop. And we saw that for our model, the concepts, when we set them to 0, actually drops. The performance drop is much higher than compared to the baselines. And this actually again shows that our model is capable of identifying more important concepts. And another thing which I forgot to tell you why we went. So this is one question I often got, that why we went to like iterative process, not end to end. So the idea is we also want to gain the sample difficulty. For example, when we use some of the sample difficulty metric, we showed that expert one or the earlier level interpretable models, they actually cover the easier samples, and as you go deeper and deeper into the iterations, the experts or the interpretable models, they will gonna cover the more difficult samples. And we actually, all these results are there in our paper, but due to the course of time, I couldn't include them in the slides.
I see. Thank you.
No problem.
Maybe